Thank you, Kate, for the introduction. My name's Oliver Watson, PhD student at Imperial College London, and I'll be talking about my modelling work investigating how genomic tools can be used to infer transmission intensity and what the potential biases in that may be. So in recent years, malaria genotyping has been suggested as an additional tool that could be used for surveillance and could help guide elimination efforts, so also in areas where perhaps surveillance infrastructure isn't as strong. And a quick rationale for that is shown below in the bottom left. So at a high transmission intensity, where we'll see a high EAR, we'd expect to see the population increasingly polygenomic. And this will be represented when we look at individuals that have a higher complexity of infection, or COI. And then as the transmission intensity falls and the rates of superinfection fall, what we'd expect to see at a population level is the infected individuals being increasingly monogenomic and COIs falling and eventually falling down to 1 on average. However, before we can use these within a surveillance framework, there are a number of issues that we need to sort of iron out related to potential epidemiological and biological drivers that could potentially bias the genetic diversity we see. And so these are some of the issues I kind of want to talk about today. And the first one is, how frequently do co-transmission events occur? So there's a paper recently out this year by Wesley Wong, which really brilliantly showed that genetically related parasites are co-transmitted. And so this will have a big impact on the genetic diversity that you see within an individual. So we're going to use our modelling framework to estimate that. And once that's been parameterized, we're going to have a look at what genomic metrics are going to be most suitable for inferring transmission intensity, so estimates like COI and clonality. And then we're going to conclude by having a look at what sampling framework we should be taking forward if we're going to use these tools. And I'll be looking at that by constructing an ensemble machine learning model and seeing what model features come out as most influential. And so the model that I've used for this is an extended version of the Imperial College transmission model that was used as part of the costing for the GTS deadlines. There's a quick overview of that on the right, was a quick overview on the right, which I don't have quite time to go over, but the main extensions that I've included is that we now track individual mosquitoes, which enables us to explicitly model recombination, which will be very important in understanding how genetic diversity is shaped. And we also characterize our parasite populations now with a 24 SNP barcode. I just want to note that it's not always the same SNPs that we decide to include within the barcode. So if we're looking at, say, a region in West versus East Africa, we'll make sure we use suitable SNPs to include within that barcode. And lastly, we've incorporated a spatial element, and so to do this, we have used rates of importation from an equivalent spatial transmission model. And so on this slide, I'm going to quickly discuss some of those extensions and highlight how we're going to estimate co-transmission event. So within our population, we'll have a number of infected individuals, and so these are represented by having a number of different barcodes, and so a different color represents a different genotype. And so when this mosquito feeds on that middle individual, the mosquito will pick up a number of gametocytes, and the ratio of those gametocytes will be represented by the relative parasitemias of those strains which we model. And so some of those gametocytes will fertilize to form zygotes, which will then undergo a couple of steps within nookinic development, starting with an initial replication, and then followed by an immediate 2-step meiotic division. And so what we see is if the barcodes are identical, there's no opportunity for new genetic variants. However, if the barcodes are different, there's potential for recombination to lead to new variants. These will then develop into oocysts, and if the mosquito lives long enough to become infectious, these will burst and a number of sporozoites will travel to the salivary glands. And so when this uninfected individual is now bitten by this mosquito, we can draw from that population of salivary gland sporozoites, which we've estimated the distribution of that from literature. And so if that individual is going to be infected, they will inherit at least one barcode. However, there were more than one sporozoite with that bite, and so in terms of co-transmission, we want to know how many other sporozoites survive to produce genetically identifiable gametocytes. So it might just not be one, it could be more than one, and this will clearly have an impact in the genetic diversity that this individual can then pass on when they are then bitten by another mosquito. And so to estimate that, we have calculated the complexity of infection, or COI, for the PF3K database, and we've done that using the real McCoyle method. And we bootstrapped over a number of different SNPs showing good intermediate allele frequencies across the study sites we're interested in. And we've also used the recorded COIs from that real McCoyle study, which was at 3 different study sites in Uganda. And then to fit to that data, we ran simulations incorporating the historic scale-up of interventions at those study sites, and we changed the frequency at which co-transmission events occurred, and then compared how we fitted the distribution of COI. And so I'm going to show up the fitting to just the study sites from the Real McCoyle paper. So this is directly lifted from that paper. And so this shows the relationship between COI and age at 3 study sites, with a blue dot being an individual COI, and then the red curve being their overall fit. And then when we carried out our fitting, this is now our model output. And so in the plots on the right, the red curve is our overall mean relationship between COI and age. And that's carried out over a number of different simulation repetitions and then also sampling repetitions from those simulations. And then the blue is just one realization of that process. And so you can see that we fit quite nicely in those data sets, and what this resulted in was an average 18% of sporozoites per inoculation event surviving to produce gametocytes. And so we can see, again, sort of good fits in a couple of the study sites, and although we slightly underestimated it in Wallakuba, which is with quite a high importation rate, the overall fits that we don't have time to show from the sort of PF3K data in comparisons to sort of population level looks at MSP2 style MOI, we're sort of happy going forward with that fit. And so we want to then move on to having a look at which genomic metrics are going to be most informative for informing transmission intensity. And so to do that, we have looked at a couple of sites in DRC and Senegal. And so what we've got on these plots is the Malaria Atlas Project prevalence for those study sites shown in the blue dashed line, and then the simulation output prevalence in the blue ribbon showing the confidence intervals from a number of repetitions. So that's just there to show that we are sort of fitting the change in transmission intensity both due to interventions and also due to seasonality. And if we then bring up the population mean COI, we can see from our model that the COI nicely tracks the changes seen within transmission intensity. And then if we have another look at, say, a different metric, so clonality, which we've defined as the proportion of barcodes that are not unique, i.e. they will be found within another individual within the population. And if we have a look at that again, so less strong sort of shifts within the seasonality, but ultimately again show the same pattern. So if we look at, say, T's in Senegal, we'll see that as the prevalence falls very low, the clonality goes closer to 1, suggesting that most of the parasites are to be found within another individual within the population. However, on this slide, we've only looked at the population mean for these different metrics. So that's not going to be very operationally useful. So we wanted to then have a look at what happens if we sample, say, 50 individuals at a time point. And so we looked at Kufa and Benin for this. And then when we looked at that, however, it's considerably less clear. So there's a lot of variation, there's a lot of noise. You might, if you look at it sideways a bit funny, you might pretend that you can see trends there, but ultimately it's not as informative as before. However, if we knew the age of the individuals within that sampling framework, then we can actually start to tease out some better patterns. So if we look again at that data, and so the black here is again just that prevalence, and what we're going to do now is stratify those samples by the mean age range seen in them, and then we're going to plot the COIs in these discrete age bins. And if we do that, we can start to recover again good informative estimators of transmission intensity using COI. And so we can see from this that different age ranges are going to be more predictive. And what this means going forward is that both A, you'll need to have an awareness of the age of your individuals that are being included, and also that it's probably going to be useful to have a range of ages included as well. And so to kind of conclude and finish on identifying this optimum sampling framework, and so to do this more rigorously than just sort of looking at some of the patterns in the age ranges, we constructed an ensemble machine learning model, and we put in as the input data, or the model features for that, these age-binned measures of COI and clonality. We also had a look at symptomatic to asymptomatic ratios and percentage of monogenomics. And we also had a look at including with the actual seasonal data which the samples were collected, because this is massively important if you've got a highly seasonal area. The inspiration for a lot of these specific metrics came from the Rachel Daniels study in 2015 looking at T's, so thank you very much for that. And so to then train this model, I carried out tens of thousands of simulations spanning a range of epidemiological settings within Africa. and then from those sampled monthly intervals for 50 individuals. And then I used a k-cross validation to split that data set up so I could then train my model, and then I tested its predictive performance against other simulations and against those, again, 3 study sites in Uganda, because for those study sites I had an appreciation of what was the age range and the timing of those collection. And so I'll show up the prediction from that. So we have the model predicted PCR prevalence against the observed PCR prevalence. So you can see a very strong fit to other simulation data. We can also see a good predictive performance against 2 of the study sites, and then Wanakuba, which had that sort of quite high COI that we weren't able to estimate sort of outside that. However, I don't want this to be the takeaway message of, we could use this in this kind of model. The most important thing from my point of view is that if we had a look at the process which was undertaken in terms of the feature engineering, we found that to create the most predictive models, it was essential to have good age range coverage, as well as including both asymptomatic and symptomatic individuals. And so this can hopefully then start a discussion as we move forwards as to what people we should be including, and then actually can we start using these tools for inferring transmission intensity. And so just to conclude, sort of started with that estimation of the frequency of co-transmission events, and that then can sort of give us an indication of sort of genetic diversity as a result from that. We then saw that genomic metrics such as COI and clonality are indicative, but to make the most of those within a predictive framework, it's really important that we both have the necessary metadata annotation, so that's the age and the timing of that sequence collection, but then also the fact that we cover the full age range and symptomatic profile of the population. Just quickly just want to finish and thank my supervisors at Imperials, specifically Bob Verity. He's been brilliant at handling my general ineptitude. And then also the malaria modeling group as a whole. Thank you to Shahan at Harvard for helping send over the real coil SNP data, and the PF3K project community as a whole. And also just want to thank those 2 papers I mentioned by Wesley Wong and Rachel Daniels, because that's been most of the inspiration for the work I've just presented. Thank you very much.
We have time for a couple of questions.
Hi, very nice data. A question, you had, of course, whole genome sequencing, that's the best data to do this work at all to start with, but the reality is that we have tons of very simple genotyping data sitting around and still being generated sometimes, like MSP2 genotyping, very simple protocols. Can you comment on whether it's feasible or not to aim for anything similar if you have much less good genotyping data than whole genome sequencing?
Yeah, 100%. So it's a really good point, and it's the reason I decided to look at just a sort of 24 SNP barcode as opposed to parameterizing it against whole genome sequencing, is because if we're trying to make this an informative predictive tool on a kind of like real-time useful metric, we need sort of maybe slightly simpler turnaround times on those measures. And so yeah, the MSP2 style genotyping does was quite useful actually. I'm somewhat prepared for that. Yes. So we sort of had a look at sort of how the measures we predict from COI compared to, say, measures of MSP2 MOI. And something that was quite interesting from our model is because we can see every single strain within the population. Obviously, that's not what's going to happen in a field setting because you've got the limits of detection. And so we had a look at some of the work that Ingrid Felger's lab has done in sort of determining that detectability. And it can still be very informative having your MSP2 measurements and your sort of simpler measures, as long as you understand what the limits of detection are when you're actually collecting those. So having an appreciation of, say, perhaps also the parasitemia of those individuals you're including, and thus what the mechanisms you're using as well.
Right. Nice talk, Ollie, thanks. I don't really have a good intuition for why, oh, that's better. I don't really have a good intuition for why in adults the COI is much better correlated with the transmission intensity than in children. And I was just wondering if you had you'd be able to comment on why that might be the case.
Yeah. So I had sort of thought about that, and I think the reason that it came out in the model as sort of being useful is, or why they have that higher COI, is just that in the model over time, due to exposure, an individual's immunity will increase, and so the chance that they then produce a symptomatic infection and thus will potentially seek treatment falls. So if they're not producing symptoms, they're not going to seek treatment, they're not necessarily cleaning out their parasite population. So they're more likely to start accruing more infections. And that's also combined with the fact that within the model, we have a sort of age-dependent exposure factor. So as you increase in age, you're more likely to be bitten in comparison to, say, younger individuals. And so that sort of explains why you get sort of overall increase in the number of strains that might be harbored within an adult population. However, that's not necessarily going to be fully evidence of why they're a good population to sample, because again, you have this issue of limits to the detection. So adult populations, on average, you actually see lower sort of COIs or MOIs than, say, if you look at children between the ages of maybe like 5 to 10. And that's kind of, again, just due to that limit to detection. So it'll, depending on what tools you've got available to how you can actually sequence and assess the genetic diversity of these individuals, it might depend actually what, again, individuals you want to be including within that sampling framework.
Thank you.
Yes.
So I'm going to introduce our next speaker, Prabin Dahal from the Worldwide Anti-Malarial Resistance Network.